did a research fellowship in clinical pharmacology where I dealt with a lot of experimental drugs and gave like experimental drugs to people, and I received experimental beta blockers and different things. But my boss, the first study that I did, my boss is a very famous pharmacologist. He's like editor of a big pharmacology journal. He was at Vanderbilt, a very well-known guy in pharmacology. But he was not the kind of guy who I don't think ever took care of patients. He just was like lab smart, but not patient smart. But I went to talk to him, so I have a tremendous amount of respect for him. I'm just finishing up my anesthesia training, and I go to him, and he said, first thing he tells me, he said, I want you to take these people who are sick, and I want you to put a catheter in the brachial artery, and we're going to measure their forearm blood flow, and I want you to infuse epinephrine through it. And I'm looking at him just thinking, he's never even started an A-line, and he wants me to put a brachial artery A-line in it and give people epinephrine. And it was just kind of, he mentioned like there was an oncology fellow, and there was somebody else who would refuse to do this, and I'm thinking, well, maybe. But it turns out that someone actually did that, and it's when the 1950s, when people were trying to figure out how catecholamines work, and they had these compounds, like they do adrenaline and they had noradrenaline, and they knew about the compounds, but they had no idea what they did. They knew that if you gave a dose to people, you got a fight or flight response, but they didn't have any idea about receptors or anything. So there was a key study that was done, and this guy in like the early 1950s, he measured blood flow to the forearm. So he measured the amount of blood that was flowing into the forearm, and I actually did this study. After seeing that had been done, ended up doing probably 30 or 40 of these. But you measure blood flow to the forearm, you put a brachial artery catheter in, and then you give small doses of epinephrine. And if you measure blood flow, initially the epinephrine doesn't do anything, but as the dose of epinephrine gets bigger, initially the blood flow to the in the forearm goes up, and then as you keep going up and up, the blood flow comes down. So, when people were looking at this, the first people that did the study, just tried to figure out like why would you give a drug that would initially cause the blood flow to increase in the forearm, and then cause, and this was a nice way to measure isolated organ blood flow, and then make it go down. And how could you explain that effect? Like if you know what you know now, what would you say is happening? Well, there's a certain amount of blood being pumped through the heart, right? And it's, if you have more blood going to the forearm, what's happened is that the resistance going into the forearm has been decreased, right? So you got like some kind of vasodilation here, right? So initially there's like vasodilation, and then at here there's constriction, okay? And people initially they didn't know what to make of it. Then they said, well, there has to be two places that epinephrine works. And they called they were coming up with the idea of receptors, and they talked about alpha and beta receptors, and they said, this is going to be something. The low dose of epi gives you the beta receptors are stimulated here, and the alpha receptors are stimulated here. And like in the late 1960s and early 1970s, people actually isolated these receptors and were able to measure their affinity, and they found out that indeed beta receptors are sensitive to much smaller doses of epinephrine than alpha receptors. And so the next question is like, where are these receptors located in your forearm? If you look at arterioles, what are arterioles?
Leading up to the capillary veins.
I mean, they're vessels, right? They're blood vessels, and they're going to be blood vessels. Like when the blood leaves your heart, where does it go? It goes from your aorta down to your subclavian artery, or your axillary artery, your brachial artery, and then it goes down to your radial ulnar artery, and then goes to muscle. But they're big arteries that deliver blood to the organs, and then these arterioles actually determine organ blood flow. And the way they do is they can constrict or dilate, and if they constrict, they can shunt blood away from that organ, and if they dilate, they can let blood go to that organ. So if you bump up cardiac output and you shut down one organ system by constricting it, the blood will go where you need it. If you need to run, it might go to your muscles. What was found is that there were, along the course of the arterioles, there were beta receptors. And the beta receptors do what? Constrict or dilate? They dilate. They were the ones that caused the blood flow to go up. At the end of the, if you, tissue perfusion occurs where? In capillaries, right? So between arterioles and capillaries, there's something called a precapillary sphincter, right? There's a little sphincter at the end of each of these arterioles. And the sphincter can tighten. And the precapillary sphincter can constrict, and by constricting, what will it do to the organ blood flow? It will it'll reduce your organ blood flow. So this would be alpha receptors here, alpha, and it turns out it's like alpha 1 receptors. So you have conductance arteries, arteries with names like aorta, femoral artery, iliac artery, carotid artery, arteries that just get the blood from the heart to the organs. These don't change too much. You wouldn't want blood pressure to drop a lot, like going down to your iliac arteries or your femoral artery, because then there would be no perfusion to go down to your legs. So these are just very rigid. They don't really change too much. These conductance arteries give blood to the organs. The arterioles control organ blood flow, and they're able to regulate organ blood flow by receptors that they have. They have beta receptors along the course of the arterioles, and they have alpha receptors here. And then you have your capillaries, and then you have venules. Venules, which are little veins that drain from the capillary, and then you have capacitance veins, are the big blood vessels that go back to the heart. Capacitors. And these go back to the heart. And what do these do? Like, why would these be important? If you didn't have these, if every time you stood up, you'd pass out. Like, what do you think happens to keep you from, when you get out of bed in the morning, from passing out? It squeezes. What do you think would be on them to make them squeeze? Alpha or beta receptors? Alpha. Okay. It turns out that these all have alpha 1 receptors here on the venules and capacitance veins. If you think of capillaries like a Penrose grain, you know what Penrose grains are, right? Everybody. If you just blow into a Penrose grain and you don't pinch the end, it'll just flop, right? And it'll just be a floppy Penrose grain. And if there's no pressure here, there's not going to be any tissue perfusion. If you wanted, from Starling's forces, you need oncotic and hydrostatic pressure to cause tissue perfusion to occur. But if you don't pinch, if you pinch the end of it, you have resistance at the end. Then you could blow up your Penrose grain and it could distend, and then you actually get tissue perfusion. So the blood that goes out of the heart, through the arterioles, into the capillaries would, you'd have tissue perfusion if these are pinched here. And it's actually, these venules are important kind of in pinching that so that there's tissue perfusion. If you don't have this, if there's no tone here, the blood will go in, come out, go through, not just come back out, no tissue perfusion, and goes back to the heart. And if you have like septic shock, or if you give someone big doses of nitrite or other drugs that will block these things here, you can actually end up causing big cardiac output with no tissue perfusion. So these alpha receptors are kind of like, if you think of the Penrose grain, are squeezing the Penrose grain so you get tissue perfusion. So this is important here. These capacitance veins, when they're stimulated by alpha receptors, will squeeze blood to your heart and keep you from passing out. Okay. Now, what would happen? So you have an alpha receptor on these veins. Where do you think? Do you think it's stimulated? Where does epinephrine come from in the body? Adrenal gland. And norepinephrine comes from where? Yeah, it's not the adrenal. It comes from usually nerves. So these receptors, do you think they see epinephrine that's been released from the adrenal gland, or do they see norepinephrine that was released from nerves on these veins? They see, actually, you don't get like a big episurge when you sit up. This is like norepinephrine that's released from the nerves that go to these veins. If you were to give someone a spinal anesthesia and block those nerves, what would happen? When they were to sit up, they wouldn't constrict, right? Yeah, they become hypotensive and collapse. If you gave someone an alpha-1 blocker, you would also get that orthostatic hypotension, right? If you are going to do OB anesthesia, who did OB? You did OB. Anybody else do OB? Before you do epidurals, what do you do for people having epidurals? You give them fluid, right? Yeah, you bolus them up, because what you're going to do, as soon as you give them an epidural, you're going to block all of these nerves, and these are going to dilate. And if the way you can keep your patient from becoming hypotensive, because you don't want her to be hypotensive, you want to keep your baby's tissue perfusion, placental perfusion up, is to make up for this lack of tone, you add more fluid to her vascular system, so you tank her up. So before you do your epidural, you would tank someone up with half a liter to a liter of IV fluid. Okay. You understand any questions about this here? This kind of basic physiology of where these receptors are. Okay, we're going to talk about epinephrine and make sure. Where's the epinephrine? Where does epinephrine come from? The adrenal gland, and the adrenal cortex or medulla? Medulla. Yeah, the adrenal medulla. What comes from the adrenal cortex? Yeah, different steroids. Sex hormones, glucocorticoids, mineralocorticoids, all come from the adrenal cortex. So let's talk about epinephrine. Where do you get? What are amino acids? The purpose of we need amino acids to eat, right? I mean to live, right? What do we do with amino acids? We make proteins with it. What else do we do with amino acids? Besides proteins, we make neurotransmitters. Okay. So if you want to make epinephrine, you have to start with something. You don't start with just carbon and hydrogen and oxygen and nitrogen. You start with a precursor, and you start with an amino acid. And what happens is you eat protein. There are protease enzymes that break down the proteins into the amino acids. The amino acids are absorbed. The amino acids circulate through the body. They're taken up by tissue, and they become the building blocks for a lot of different things. Proteins, but most neurotransmitters. And we're going to be talking about epinephrine in the adrenal gland here. So this all starts with an amino acid. Amino acids, just to go over a little bit about their. Why are amino acids called amino acids? They have the amine group here and the carboxylic acid here. So this is amino acid. Amino amino acids are joined to other amino acids, they join one to the other by taking a water molecule out, and then protease enzymes break them apart into their amino acids. So you eat protein, you break it apart in the stomach with protease enzymes and acid. You break them down to amino acids. Amino acids get into the body. Do you think they're polar or non-polar? They're polar because they can exist in this form here. I mean, this is can be a negative charge and these positive charges. So these are polar molecules. Do you think they go past the blood-brain barrier or not? No. And what about going into cells? Choline, which was polar, couldn't get into cells. You know, these aren't easily getting into cells. How do you think, if they're so essential for living, how do you think we get them into the cell and past the blood-brain barrier? Yeah, there's active transport proteins that do that. Now, amino acids exist in two forms. You can draw this as you can have the hydrogen going backwards or the hydrogen coming forwards. And if you put these in water and you measure which way light is bent, one of these will bend it to the left and one will bend it to the right. And they call, there's a dextrorotatory and a levorotatory form, but the ones we're interested in are L amino acids. It means they're all stereoisomers. You don't have to, you just know that, like when we talk about amino acids, we talk about L compounds. When you treat people with Parkinson's, what are you giving them? L-DOPA. What does L mean? It's levorotatory. Okay, so it's a term you see. You're going to see it in local anesthetics and things, but it just means that instead of a mixture, a racemic mixture, these two, like you could have racemic epi, which we have. Racemic epi is the L and the D form, or else you could have like a pure form like L-DOPA, which is just an L form. Okay. Okay, what I'm going to talk about now is on figure 6.3 on page 71, and it's also in the other books. There's a picture. I checked all three of the books I recommended, or you can go on the internet and find a picture that here it's titled Synthesis and Release of Norepinephrine to the Adrenergic Neuron, but we're going to be talking about epinephrine. I want to talk about three related compounds here. Hopefully. This is phenylalanine. Again, those structures are important, but this is an amino acid, and it has, this group is the R, CH2 with a phenyl group. It's called phenylalanine. Phenylalanine is used to make certain compounds and proteins, and it's an essential amino acid. This is hydroxyphenylalanine, but we call it tyrosine. But it could be called hydroxyphenylalanine. And this is an essential amino acid. Okay? And this is dihydroxyphenylalanine, and we call this DOPA. And this is not an essential amino acid because we can make, there's an enzyme that will put this hydroxyl group on this compound to make, if you have tyrosine, you can make L-DOPA from L-tyrosine. So these are all amino acids because they have this, the amine and the acid group. But these two are essential amino acids, and this is a non-essential amino acid. Okay, so what happens is tyrosine circulates. You ingest proteins, you break it down, you have tyrosine that's in the blood. Tyrosine circulates. We're talking about the adrenal gland. So when tyrosine comes to the adrenal gland, it's taken up and it goes into the cell. And when it gets taken into the cell, it becomes a precursor for all catecholamines. Okay. The first thing that happens to tyrosine, and this is this will show up like it has, I know in the last 3 or 4 years, showed up in a couple of board exams. There's an enzyme, tyrosine hydroxylase. And this enzyme is a rate-limiting action that converts tyrosine to DOPA, dihydroxyphenylalanine, L-DOPA. Okay? And so what happens is that you just put a hydroxyl group, this enzyme, tyrosine, and it hydroxylases, it puts this group here. There's another enzyme that is called DOPA decarboxylase. I don't have to know the name of this, carboxylase. And some people call this aromatic amino acid decarboxylase. But what it does is it takes off this carboxyl group. This enzyme takes off this carboxyl group right here, and it converts DOPA decarboxylase to dopamine. Now, if you were dealing with like a certain nerve, brain tissue, this might be the only enzyme there is, and this might be the end product of this this pathway. But in the adrenal gland, you want to go toward epi. Because epi is the adrenal hormone, main circulating adrenal hormone. So dopamine can go from dopamine beta hydroxylase. And it puts a hydroxyl group right here. What's the difference between norepi and epi? Yeah, which one has a methyl group? Which one has a methyl group? Epi. Okay, which of these compounds here are amino acids? This is, right? And this is, right? Is this an amino acid? No, and is that an amino acid? No. So this is norepi. And what do you think happens when norepi goes to epi? What do you think happens? Yeah, it adds the methyl group to the end. So, there are different enzymes. Depending on what enzymes are in this particular cell will depend what's made. If you don't have this enzyme here, you're going to end up making norepi. If you don't have this enzyme or this enzyme, your cell will make dopamine. Okay, but in the adrenal gland, and only in the adrenal gland, when tyrosine comes in and it starts to be metabolized, the end product is epi, and then epi is released into the circulation. Okay, so and this is in your book. I mean, if you, this pathway, you don't have to know any structure, but this pathway is book. The epi is then released, and when your nervous system stimulates your adrenal to release epi from your adrenal medulla, it gets dumped into the systemic circulation. It goes throughout the body, and it stimulates alpha and beta receptors throughout the body, right? And the effect that it has depends on what organ system it circulates by. If it circulates by the heart, what does it do? It causes increased heart rate and increased. It has a positive inotropic and a positive chronotropic effect. If it look on page 73 of your book. If it when it goes into the blood vessels and arterioles, what can it do?
Constrict.
Yeah, it can either constrict or dilate, right? Low doses will dilate, higher doses can constrict. When in the venules, it can constrict, so it makes more blood available, like during the fight or flight response, to be pumped by the heart. The pupils are going to dilate or constrict. Dilate, right? You get mydriasis, you get pupillary dilation, would you expect to be storing energy or breaking down energy? Right, so you'd be mobilizing glycogen, breaking down fat, and you would be inhibiting the effects of insulin, right? And if you look on this chart on page 73, it describes those effects of adenoreceptors. I'm not going to ask there are no questions about lipolysis or effects of these on, the effects on the liver and, insulin is not something that, I would be interested in you guys knowing its effects on arterioles, on venules, in the eye, and other organ systems, but you don't have to worry about insulin release or other things. In the kidney, epinephrine can cause, through beta receptor stimulation, beta 1 receptor stimulation, can cause renin to be released. And if renin is released, you get sodium retention, and things happen so that you're going to increase blood pressure. Other beta effects are, it can give you decreased peripheral resistance through effects on the arterioles, the vasodilation on the arterioles, bronchodilation or pulmonary effects of epinephrine, the beta effects on the lungs of bronchodilation, and it gives you relaxed uterine sleeve muscle. It can block uterine contraction. When you look at the effects of epi, or all of the adrenergic receptors, notice that the beta 1 receptors are only located in 2 organs. They're the heart and the kidneys, the 2 ones that we're concerned with. So all the other beta effects are not the heart and the kidneys. So the heart and the kidneys are important for maintaining blood pressure, and those are beta 1 receptor effects in the heart and the kidneys. Okay. In the everywhere else where catecholamines are made, they're released from nerve terminals, and they're either going to be norepi or dopamine are going to be the catecholamines that are going to be important that you'll see. But in the autonomic nervous system, like we saw, in the heart, is norepi, which is released by the nerve terminal. The postganglionic nerve terminal is norepi, which is released that stimulates the beta receptor in the heart. There's an important thing relating to their metabolism of these drugs and their action. If you have this structure here, where you have 2 hydroxyl groups on a phenyl group, this is a catechol. So this is called a catechol, this is a catechol, this is a catechol, this is not a catechol. This is a catecholamine, and here's the amine group. This is a catecholamine. So we call these catecholamines. Epi is a catecholamine. Okay, but this catechol is an important part of the structure of these compounds. It's this catechol portion of the compound.
So what makes it a catechol is number of...
This right here makes it a catechol.
Okay.
If it has these two, this is not. If this had a hydroxyl group here, it'd be a catechol. But because it's not missing that hydroxyl group, it's not. You have to have a phenyl group with two hydroxyl groups like this attached to be a catechol. And these are catecholamines. Now, I'm going to need part of this. So let's look at figure 6.3 as it's drawn in the book and talk about what happens. We'll just refer to this. So if you have the this is a nerve that's releasing norepinephrine. Is what's the name of this nerve? It's a sympathetic fiber. It's a post-ganglionic sympathetic, and this is a nerve terminal. Okay, so this is post-ganglionic nerve terminal. It's going to release norepi, and we'll stick with the heart. We can talk about the heart. The norepi will interact with beta-adrenergic receptors here in the heart. It may react with other receptors, alpha receptors in the precapillary, in the precapillary sphincters or other places in the heart. It's reacting with beta-adrenergic receptors. Norepi is stored in vesicles. So, what if you look at the picture that is in page 71, it's basically this picture right here. Tyrosine is the precursor of catecholamines, and in this, we're dealing with norepinephrine as a catecholamine here. Tyrosine has to be taken up into the cell by an active transport process, and it goes into the cell. It's converted by tyrosine hydroxylase to DOPA. DOPA goes to dopamine, and then dopamine goes into vesicles where it's converted to norepinephrine, and then norepinephrine is released, and then when it's exocytosis, it can be released and it can stimulate the beta-adrenergic receptor here. There's a couple of things related to metabolism of these drugs that's going to be important. One is that there's an enzyme in mitochondria here. It's called MAO, and it's a monoamine oxidase. And the MAO can metabolize dopamine and norepinephrine. And what it does is that this enzyme, it basically chops off this part of the drug, like So what it does is in exchange for the CH2 amine group, you get COOH. You just, MAO breaks down this part of the drug here. Okay, so now this enzyme can metabolize the dopamine here, but once it gets in the vesicle, the enzyme, this is kind of protected. So by being in the vesicle, the dopamine, the norepi, and the norepi here are not able to be metabolized by the enzyme, but in the cytosol here, any dopamine or norepi that's there could be metabolized by this enzyme, and it's basically inactivates this drug. Once it gets metabolized to this, it's no longer active, it's removed from the cell, and it gets excreted in the urine. Okay, so monoamine oxidase is an enzyme that metabolizes this drug right here. Other parts of this that are important are, we talked talked about how acetylcholine wears off. You know, how does norepi wear off? Norepi can wear off 3 different ways, okay? It can diffuse away. It can be taken back up into the cell through a reuptake protein that's here. So it gets recycled so that when norepi gets, it can be taken up into the cell. It's susceptible to being metabolized until it's packaged in vesicles. So it can go in here and kind of make it in the cell and then be metabolized away. And the third way is that there's an enzyme called COMP. And COMP is equal to catechol O-methyl So with COMP, what you do is you would take this is a catechol, so this is a catechol here. So it's catechol O-methyl. Here's a O position. This is para. This is ortho. The O-methyl transferase. So it transfers a methyl group to this hydroxyl group here, and it makes a catechol go into this. So norepi can be metabolized by catechol O-methyl transferase, and it becomes inactive. Okay, so there's 3 ways that epi, once it's stimulated the receptor here, the beta receptor in the heart, can quit stimulating the receptor. One is it can just diffuse away and it's gone. The other way is it can be metabolized by catechol O-methyl transferase, and the third way is it can be taken back into the heart. Okay, the number 1 way it wears off is by diffusion away. Okay, notice this is extracellular here, and this is intracellular. Okay, so and this catechol O-methyl, once it's methylated on that catechol part of it, it's inactive and it gets removed in the urine.
Broken down by the MAO again?
It can be broken down by MAO,
Or it can be repackaged.
or it can be repackaged. Yeah. There's several drugs that can block this process. Cocaine is one, and imipramine is another. There's other ones, but we're going to talk about cocaine and imipramine. If you give someone cocaine, and what's going to happen to the norepi here?
It's not gonna be real.
Yeah, I mean, it's going to hang around longer. Yeah, some will diffuse away, some will be metabolized, but a lot of it that was taken up is not going to be taken up. So this concentration is going to be enhanced, right? And if this is greater, then what are the effects you're going to see in the heart?
That's why accelerated heart rate, chronotropin.
Right, yeah, you'll get increased heart rate, increased inotropy. In the brain, it gives you different effects. You know, whatever the norepi is doing in the brain will give you the vagal effects there. So this is a transport protein here that's responsible for taking norepi back into the cell, and it can be inhibited by cocaine and imipramine, and that's just a important drugs in their mechanism of action. There's other drugs that work on this process. Some drugs will enhance the release. They'll go into the cell and displace norepi and cause norepi to be released. So what would they do? What would be the effect there? right, and if you, so you'd have an enhanced effects of norepi, and drugs, I don't want to mention drugs that aren't going to be on your test. There's, here we'll just use but there's Sudafed, ephedrine, amphetamines. Okay, will this be a direct or an indirect effect? This would be an indirect action. It goes in there and displaces, and indirectly by displacing it, you enhance the catechol effect. So ephedrine, which we use for blood pressure control, Sudafed, and amphetamines can affect the norepinephrine in vesicles to be released, and you get more norepinephrine here. There are other drugs that can work here, beta agonists. And some beta agonists at work would be like dobutamine,
What do you mean by displacement?
these drugs can go into the vesicle and actually take up the space that the norepi is in, and causing norepi to be released. And it actually ends up causing more norepi to be displaced here. But the only I don't want to talk about drugs that aren't going to show up, but dobutamine works by directly stimulating. If you give someone dobutamine, you're giving a drug that directly stimulates the beta receptors. So you can give a beta agonist that works directly, you can get one that works indirectly, and some of them are mixed, like some ephedrine's effects are indirect, and some of the, indirect here, and some are direct, a little bit of effect on the receptor, a little bit of its effect is from the release of norepi here. So when you give a drug, you want to know, am I giving a drug that's a direct acting drug, or am I giving a drug that's an indirect acting drug? These kind of work indirectly. This is a direct acting beta agonist.
Do you want us to know the drugs that have mixed action?
You need to know Sudafed, ephedrine, amphetamines, cocaine, imipramine, and dobutamine.
So, of all three, the first class is the butamine is the direct acting, the others are indirect.
Right. Yeah, they produce their effects indirectly. And these questions are going to be like big concept questions. It's not going to be like really picky trivia questions. It's like in the same way I'm going over here is the way I'm testing. I'm going to beat you up with trivia on these drugs. None of it is in the book that I didn't talk about.
Ephedrine is both indirect and direct?
Right.
Always? Or is it dose dependent, or?
I'd say, in doses at work, it's both. So we're gonna talk about agonists and the antagonists next, but then we're gonna come back and talk about the Parkinson's drugs, and we're gonna hit this again. We're gonna see this again, and you'll see other things that may make this clear to you. But the picture that's in the book, the important things: know that you start out with tyramine. Know the rate-limiting enzyme is tyrosine hydroxylase. You go to dopa, dopamine, it goes into a vesicle where it's protected. You have an enzyme that breaks down the drug in the cell, it's called monoamine oxidase. You have an enzyme that breaks down the drug outside the cell, it's catechol or methyltransferase. And you can meet in its reuptake, it's taken up. You can block its reuptake. You can enhance its indirectly get effects. You can produce effects directly at the receptor with either drugs like dobutamine or mixed drugs that will do both of these.
All right, one last time, the tyrosine hydroxylase does what now?
It's a rate limiting step.
So it
Here's
slows it
the,
down?
yeah, what if, here's the problem, is like, what if, like, if you were to eat a steak and, absorb a lot of tyrosine and it goes into your, it's absorbed here and it goes here, if there was nothing that would limit the response, then you would, take it in and, like, all of these enzymes, once you have dopa, it's automatically converted here. Once you have dopamine, it's automatically converted. These enzymes will convert whatever's there. This enzyme is regulated, and if it wasn't regulated, you know, you'd eat a lot of tyrosine, and then you produce your blood pressure go up. This is the way your body controls this. We're gonna we'll take a little break and come back and talk about alpha-2 receptors and antagonists, to this in the next section. But this is important for modulating like your response. Steroids will enhance the effects of this. You can inhibit it. We're going to, at the beginning of the next talk, we're going to talk about alpha-2 receptors and also feedback inhibition here. But there's ways of controlling this, and you control it at the first step. The first enzyme is the one that you want to control. But it doesn't matter what the activity of all these little enzymes are, the amount of all of these is dependent upon whether this is turned on or not. If it's turned up, you're going to get a lot of this. If it's turned off, you're not. None of these other enzymes regulate this process.
And the MAO, what does it do again?
MAO is a monoamine oxidase. It chops off, it oxidizes this part, and it converts this right here to a COH. It just metabolizes. The molecule, it has two ends. It has a catechol end, and it has the amine end. This end is metabolized by the catechol methyl transfer.